Okay, so let's start part 2 of our lecture on material extrusion, and we'll pick up where we left off. We just finished talking about high-performance materials, especially those that are with the Stratasys 3D printers, the FDM 3D printers. And that leads us to the next part of this discussion, which is we're going to look at the 7 basic principles of material extrusion, okay? And these go in order too, that is in order of the 3D printing process of material extrusion. But these are the underlying fundamental principles that guide each one of these steps. And so these are material loading, liquefaction, extrusion, solidification, positional control, bonding, and then support generation. Okay, so we'll take each one of these individually. So let's start with material loading. All right, so the material is fed as a continuous filament in all material extrusion printers. All right, typically the material is on a spool, as it's shown here. Spools are different sizes. Spools also have a different diameter for their filament. Okay, some spools are contained within kind of proprietary sealed containers that, for example, in the Stratasys machines, the spools of material come with containers that have barcodes so that you can only use Stratasys materials for those. Other 3D printers, especially the more home-based ones or the lower cost ones, have a very open source kind of methodology to the filament. It is also possible that you can make your own filament through recycling of any of a number of thermoplastics. Okay, the filament on the spool is fed into the extrusion area by a tractor feed system. Okay, that means that there's some type of a wheeled mechanism or geared mechanism that is going to kind of pull the filament through the head and on to make the depositing of the material possible. The second principle is the liquefaction principle, and this is the principle that underlines the change of the filament from a solid to a liquid. Okay, so in this area, the filament is going to be heated to a semi-liquid state, right? It's not going to be completely liquefied, but it is going to be what we would call a plastic state. Now I want to differentiate between the term plastic as in material and plastic as in a phase of a material. A plastic state is for a material is a state of the material where it's pliable, it can be stretched, it can be molded and manipulated, but it's not a liquid. Okay, so it's kind of in that in between the solid and the liquid stage, and that's what we're talking about here with the filament. To do this, heat is applied to a chamber, right? And so you can see the chamber here via heating coils. Okay, so these coils kind of wrap around the area where the filament is going to be fed. So you can see this is the tractor feed system that's going to be pulling the filament and directing it downward through the heated coils. Now, the reason why we have 2 filaments here is because we have the build material. That's the material that the object is going to ultimately be constructed from. And some printers, especially the high-end printers, also have a support material. Okay, and the support material is what you're going to use for all of the supports. Okay, not all 3D printers have support material, but that's a different issue. So heat is applied through these heater coils, and as the filament is moving through this, the heat applied to the heater coils is going to heat it up just enough so that it is at the right consistency. So it's going to basically come out of these extrusion nozzles and be deposited layer by layer onto the build platform or onto the previous layer. The material is kept in a semi-liquid state at the lowest temperature possible. Okay, so that means that it's just above the melting temperature, right? So again, we don't want to melt it. Melting means we're turning it into a liquid. So let's say the melting temperature is 100 degrees Fahrenheit, right? We want to keep it at 99 degrees Fahrenheit so that it's not going to melt, but it's as close to melting as possible, because that's going to give us the most control of our extrusion process. All right. The third step is the extrusion. Okay. And actually, what I have here is the patent drawing for the nozzle where the extrusion occurs. Okay. And again, none of the parts here are labeled. They're numbered according to the patent, but we can still kind of discern what most of these do. So we have the wheels for the tractor feed system. This is the filament going down into here, and you can see our transition from a solid to a semi-solid or semi-liquid state, that plastic state right in there. These are the heater coils right here. Okay. And this is where the extrusion is going to be, or the material is going to be forced through this nozzle and extruded onto the previous layer. Okay, the nozzle diameter determines the shape and size of the extruded road. Okay, so this is a term that we want to start to incorporate here. Extruded road, the line that the filament is extruded into, right? We call those roads, right? So this down here towards the bottom, you can see a different accumulation, different configurations of extruded roads making walls. Okay. So the nozzle diameter is going to determine your minimum feature size, right? So we can't extrude anything less than the nozzle diameter, right? Think of a toothpaste container, right? When you squeeze your toothpaste container, you're going to get a diameter of toothpaste that comes out. Now, you can't squeeze the toothpaste and get less than a full diameter of the toothpaste out of that nozzle, the toothpaste nozzle. The same thing goes here, okay? So the nozzle diameter determines the minimum feature size on your part. So if you're designing parts that you intend to 3D print, and you have features that are less than the nozzle diameter, well, I hate to tell you, but they're not going to print at the size that you designed them at, okay? FDM, or the material extrusion process, is best for large parts. All right, that is wall thicknesses greater than or equal to 2 times the nozzle diameter. All right, so if we look at the walls down here again, right, just having a wall made up of one road thickness is not going to be very stable. I think you can imagine this, think of trying to build this out of, some kind of, structure, with, like maybe rolls of carpet, right? So you roll up a carpet and then you roll up another carpet and you put that carpet on top of it, on top of the first one. You can imagine that this top one is not going to be very stable. Okay. And so the lack of stability is going to affect accuracy. It's going to affect the deposition of the next layer. So there's all kinds of domino effects that are going to be caused by having this wall being too thin. So the minimum stable wall is going to be 2 beads or 2 rows. Okay. A better wall would be more than 2 beads or 2 rows. All right. We already talked about the tractor feed and the pinch roller system. All right. And variable feed rate is going to be important. All right. So we do want some control over the feed rate. We don't want a constant feed rate. So the material is just going to come out at a constant speed, because that's going to affect where and how the deposition occurs. So the tractor feed system, or the pinch roller system, whichever it is, needs to modulate according to the geometry and the state of the 3D printer and what's being printed at that moment. Moving on to principle 4, solidification. All right. So what solidifies the material? Remember, we have a plastic material, that is to say it's semi-liquid or semi-solid, whatever you want to say. It's stretchy. Let's use the term stretchy. What is going to turn it back into a solid material? Gravity and surface tension is going to affect the material in a negative manner, right? So gravity obviously is going to try to flatten the material as it comes out in its molten or squishy state. And surface tension is also going to affect it negatively. These are things that we need to control, especially when we're printing fine features. The material may also shrink when cooling, okay, which again is going to have a negative impact on the dimensional accuracy and subsequent layers if the shrinking is too great, or if you're building a large object. And so as the shrinking continues, it's going to affect more and more of the layers. The minimum temperature differential to reduce shrinkage is what we want. Okay. So again, we want to control the temperature very finely so that we're 1 degree above melting point, 1 degree below the melting point. We want the temperature, in the area where we're 3D printing and of the material itself to be very close to that melting point. All right, so that we can control whether it's melted or whether it's going to it's going to revert back to its solid state. Okay, so we also want to ensure gradual and slow cooling to minimize some of these negative effects, especially the shrinkage. All right, so we can control the shrinkage by not basically having such an extreme temperature differential across our part as it's being built. All right, this goes to a lot, both the solidification and the liquefaction goes to a lot of the effects that we see and how we try to minimize them by using a heated chamber. So as I said, the 2 Stratasys machines we have at the Moraine Valley Community College 3D printing lab both have heated chambers. And those heated chambers, the temperature is controlled very closely. The cooling and how it's cooled are also controlled very closely, right? So we want the heated chamber to basically be as close to the melting point as possible without going over the melting point. All right. And that's going to keep everything kind of in a comfortable zone so that we don't get drastic shrinkage. Another thing that I should add with this is that, at least one of the 3D printers, Stratasys 3D printers, can only print ABS. ABS is notoriously temperature sensitive, and it needs that heated chamber. A lot of the home 3D printers print other materials such as PLA, which does not need such a finely controlled environment. However, I will say there can be negative effects if you have, let's say, for instance, fans that are blowing across the surface bed, the build platform, as the material is being 3D printed. So you want to reduce that as much as possible. Controlling that environment around the part being 3D printed is critical. All right, so moving on to positional control. This is how the 3D printer is basically printing each layer. All right, and it's not just a matter of tracing out the layer that you design in whatever 3D CAD model you're using. All right, we have to know what's going on with the perimeter, how the perimeter is being deposited. We also need to know how it's going to handle holes or islands in the part, and what's going to happen on the infill, right? The infill is the area where basically it's the area inside your part, right? And in this diagram over here, you can see 4 examples of infill. Now, in actuality, there's a wide range of infill patterns, right? But the 4 here are indicative, are good samples of what that is. on the top right-hand corner, we see a solid infill. Okay, so this is basically, we're just going to fill the material with liquid, with the 3D printer material. Okay, then as we move across to the left, going in a counterclockwise manner, we see kind of a triangular shape pattern. Moving down here, we see a square pattern where the squares are kind of aligned on a 45-degree angle. And then over here, below the solid is another square pattern, but the squares are slightly larger. So the infill pattern can affect the weight, it can affect the strength, it can affect, all kinds of different factors here. And so the printer needs to know how you want it to fill the inside of the part. All right. There are also, we talked about in the last one, variable feed rates, and these are areas where we want to control the feed rate, right? So the perimeter, we want a relatively slow flow rate. Also for islands and holes, we want a slow flow rate. For the infill, we want it to be fast, right? This is not a dimensionally critical area. We just basically want to fill that area. And so a fast flow rate is going to benefit us there. We also need to know how we're going to stop and start each layer, right? And that's going to develop into seams in the part and how we handle the seams. We need variable flow rate additionally for directional changes and to counteract print head inertia. So this is one issue that comes up when you're changing directions on the print head. The print head, because it has mass, is going to have an inertia. All right. And so you can imagine, let's go up to this figure. If we're printing across here horizontally from left to right, and then we very abruptly need to go at 90-degree angle downward, the print head, because of the inertia, is wanting to go across here left to right, and it's going to inevitably shoot past a little bit before it comes down here if it's moving too fast. And so what we want to do is we want to slow the print head. But when we slow the print head, that means that we need to slow the flow rate. All right, because we want a constant flow rate for this wall that we're building, the perimeter. And if we slow the print head, then we correspondingly have to slow the flow rate. So all of these things have to go into our program for how we want to print. And so now you can start to see that we go from, kind of a simple idea. Hey, we're going to squirt almost liquefied plastic onto a build platform over and over and over again to, wow, how do we need to change this so that we can make parts that look good and have dimensional accuracy? Speaking of seam control, right? And I bring this up because it was interesting that there was a new Stratasys patent filed in 2014 to control seam visibility in their FDM printers. All right. And you can kind of see this is taken from the patent, all three of these figures, the flow chart and these other two figures. So what they try to do is have two separate exterior outlines generated. So the flow rate is going to go out like this around. We're going clockwise. And it's going to have a crossing here and go on the inside. And then it's going to cross again and go on the outside. Okay. So, this kind of a flow or a perimeter is going to result in a seam right here. So how do we control that seam? All right. This was a very controversial patent. Because a lot of companies, other big 3D printers said, how can you patent just how you're making the perimeter? It was interesting. So if you notice here, as we blow up this area here, the whole point was to minimize the seam right here so that you just have this little V shape. All right. So what we're really talking about here is path control. Right? Path control. How does a 3D printer work? In this kind of example right here, if we were to make this almost look like a C, right? The letter C or a annular ring with like a quarter of it removed here. So the first thing that's going to be printed has to be the perimeter. So they'll print the perimeter, okay? And what I've numbered here is 1, 2, 3. Those are the first rows that are made. So it's going to come, the printer is going to print this outside diameter. It's going to come around here, come across in this horizontal part, do this circle, and come back here. And it's probably going to do that twice to make a perimeter of 2 rows thick, okay, for minimal stability. And then it's going to start doing the infill pattern. So it's going to come over here to 1, and you can see this infill pattern is just a linear pattern. And the print head is going to move over, up, down across here, and it's going to finish this one first. So it finishes up here at 1, then it's going to move to 2, and it's going to go down like this, and then it's going to finish 2 right here, and then it's going to hop over to 3 and do this and finish at 3 right here. Okay, so actually 3 is going to be very short. I'm sorry, 3 is going to go just like that because 2 is going to fill this area right here. This is all based on this one infill pattern, right? Other infill patterns are going to have different paths that the printer head is going to have to make. So some things that we want to consider are where the seams are. Sometimes the printers will change the starting and ending so you don't have one seam going up the whole side of a part. Okay. What is the infill pattern? What is the pattern? What is the density? Is it sparse, semi-sparse, solid? What is the path that it's going to take? Where does it start and end? Okay. And you can see down here in the figure on the bottom here, how that affects the strength, right? So this is the infill, right? This part is the infill, and this is the perimeter. And you can see that if we have 2 back-to-back infills right here, we're going to have a gap in there, and that would result in a diminished strength for our part. If it's deposited and it goes a little like this, we're going to have less of a little cavity here, but we're also going to have the possibility of bulging this outer wall because we're putting material right here that may push this outer wall. So all of these things are, basically trade-offs that a 3D printer has to make. Okay. And as a printer, as a user, I should say, as a user, these are things that, that are trade-offs that you're going to have to make where you adjust a lot of the settings of your 3D printer to get the desired part. Okay. So with the overlap control, as I said, we want to avoid bulges or swelling. The gaps weaken the part, and we want to control the extrusion flow rate when we're doing this. Okay. Now, moving on to principle number 6 is the bonding principle. That is the bonding of one layer to the next, or one road of the filament to the next one. Once extruded, the material must solidify and bond with adjacent materials, okay, with the adjacent roads, as we called them. The previous extrusion must have sufficient residual heat to bond with the new extrusion. So that goes to the cooling. We don't want it to cool so much that the previous layer or the roads next to each other are going to be in effect a solid already solidified, because then that's going to reduce the amount of bonding that can occur with the current layer. Cooling too fast induces this surface fracture effect. Okay. And the last principle is the support generation. How are supports going to be generated? Where are they generated? What is the shape of the supports? And do we have a support material, or are we making the supports out of the build material? Okay. So the two general forms here are similar material supports and secondary material supports. Now, I'll tell you that the Stratasys machines that we have basically a water-soluble support. Or support material, which is fantastic. It's really nice and easy to use. Some of the water soluble support materials have to be immersed in a bath, and a lot of times there's a detergent that you can put in that bath to kind of speed up the process. And sometimes they have to go overnight. I've put parts in the bath that required up to a week of sitting in the bath. The bath that we have for the Stratasys machines has an ultrasonic vibration. It's also heated. So there's other things that you can do. Some of the support material is very easy to remove with just straight up water. Okay. Heated water may help, but it doesn't have to be boiling or anything. In many of the home 3D printers and the low cost 3D printers, the support material is the build material. And in this case, what you want to have is you want to have the supports be easily removable. So you have to control the geometry of these supports so that they can be removed without destroying the original part, the part geometry that you actually want to keep. Okay. Secondary nozzles are very helpful in this kind of situation, although they're not necessary. So there you go with the support generation. All right, so we'll finish part 2 here. The next thing that we're going to look at is some different examples of material extrusion 3D printers and how they work. So we'll pick up in part 3 at this point.